back to 8.8 here a second. These improper integrals. So I only did two kind of cool examples the other day. I guess I only did two. Here's one. Here's one. So this is not too bad, but it's different than my examples I did the other day. It's a little different. So anyway, that's 1 over the 4th root of x dx from 0 to 16. You know, the problem I did the other day, I had bounds that went from 1 to infinity, and we called those an improper integral because it had that infinite bound. And so having infinity as a bound makes it improper, and we figured out how to make it proper. Well, there's other ways to be improper. Why is this one improper? The 0 bound. And why is 0 a bad bound? Well, it's not always a bad bound, but in this function is undefined at 0. And again, we could kind of take a look at a graph if we wanted to very quickly. This graph does resemble my graphs from the other day. And it's undefined at 0. So I'm asking you to integrate from 0 to 16, and it's got this, maybe it's an infinite area, right? Maybe it's maybe it's a finite area. It sort of depends on whether it converges or diverges. It sort of depends on the tightness of this to the y-axis. Remember the other day, the problems were about the tightness to the x-axis. Because I did 1 to infinity. Those were different. This is a different problem. I'm going from 0 to 16, and I'm integrating this function. I just quickly graphed this function for you, and I think I'm kind of right. So anyway, the 0 is the bad bound. So how do you make it proper? You change it to an A or a B. You go from A to 16. And by the way, I'm going to rewrite this as x to the negative 1/4. You guys okay? And then out front, what do I have to write out front to make it proper? As A goes to 0. Now listen, I'm going to go ahead and add 0 from the right. And I'm technically correct there. And why do you think I need to put from the right?
Because you can't have a negative on the right. And
I would say it's because I'm going from 0 to 16. And if you're working from 0 to 16, aren't you working on the right side of 0? All right, so I'm not on the left side of 0. So technically, I'm approaching 0 from the right. All right, cool. So technically, we just took this and made it proper. And now I just got to do it. It's not that hard to do. It's a power rule. How do you do x to the negative 1/4? Add 1 to it, so it's x to the 3/4.
Then divide by that.
4 divided by 3. Isn't it a negative?
Let's see, you add 1 to it.
Oh, yeah.
So,
You add 1 to it, x to the 3/4. Then divide by 3/4, but you know what I'm going to say? Multiply by 4/3. Let's evaluate it from A to 16. And don't forget, we're going to do the limit as A goes to 0 from the right. So anyway, that was easy. The integral was easy. It was just a power rule. We made it. And here we go. I'm going to plug the 16 in there, and I don't have a problem with this because the 4th root of 16 is 2. 2 cubed is 8. 8 times 4/3 is 32/3. So when I plugged the 16 in there, I did all that work. I took the 4th root of 16 and cubed it. And that gave me 8 times 4/3 is 32/3 minus, now I'm plugging in an A, so I'm just going to have A to the 3/4. So there's my answer, you guys. Now what do I got to do with it? Take the limit as A approaches 0 from the right. That's actually very easy. If A approaches 0, I guess it's 0. And the answer is 32/3. Awesome. because we got a finite answer, what do I say about this original improper integral?
It converges.
It converges. That's the word, converges. Because it got a finite answer. What if I would have got an infinite answer? I say the integral diverges. It's just a term we use to discuss these integrals, whether they're finite or infinite. Converges or diverges, I guess. This one converges. And what that means visually is, again, I drew a little picture for you. From 0 to 16, there is a finite amount of area there. It's 32 thirds. Even though it seems infinite. I mean, this does never touch, and but it gets tight enough and skinny enough where we get a finite area, 32 thirds. From there to here, this stopped here. I mean, one more time, just to compare and contrast that. I did this problem yesterday, and well, from 1 to infinity, and the picture was this. It was kind of this picture, but it went from 1 to infinity. Anyway, that one wasn't tight enough to converge. This one happened to diverge, I think. Any questions?
Could you break that down into limits for 0 to 8 plus 8 to 16?
What now? Say that again.
Oh, I'll show you the first sign
Okay.
in a different way.
He was going to make it into 2 intervals. 0 to 8, and then 8 to 6, plus the interval 8 to 16.
Oh, yeah, but it's not necessary to split it up. But there might be some problems in the book where they discuss splitting this up, right? But we went from 0 to 16, and we could do that with one integral, like we did, right?
So if it was negative 16 to 0, would you just do the same thing, only 0 pushes from 1 up?
Yeah. Here's another one. Look at this problem. Negative infinity to infinity. 4 over 1 plus x squared dx. Yeah, this is classic. This is cool. I mean, this is classic, cool problem. And we can do it. But, you know, I do really love the visual representation of these things. But, you know, you can crank through them without thinking. I mean, right? We crank through this, I don't know, without thinking about the picture. But then I like you to think about the picture. So this is another good one. If you wanted to think about this picture, it would be this. You could pick up a graphing calculator and attempt to graph this. I'm going to help you because I know what it looks like. It looks like this. It's kind of a bell-shaped curve here. So that's a picture of this function, and apparently I want the area from negative infinity to infinity. Good luck. Like if you hired a painter to paint that for you, he'd be there all day, right? You're painting these little slivers. Wait, there's a little left you didn't get. You know, you have to wait. You didn't finish that. I mean, are you guys with me? This is infinite amount of skinny, infinite area, dude, from negative infinity to infinity. Now, does it come out to infinity or does it come out to a number? In other words, does it diverge or converge? Well, maybe I don't know until I crank out the problem. You know, I do it analytically. Or maybe after I get enough feel, after I do these problems a little bit, I start to get a feel for, I think if this is x squared, that's tight enough, so it will converge. If it was an x to the first, I don't think it would. But that's me giving away too much information. Hey, anyway, I guess we should make it proper. Let me show you how to not make it proper. You ready? Let's just be sloppy, improper people. You ready? So I'm going from negative infinity to infinity, and I don't care about being proper. I ain't even caring about being proper. All right? So how do I integrate? First of all, how do I integrate? So everybody's staring at that. That's the issue. It's easy.
That looks like an inverse geometry.
It's an arctan of x. Like, you just got to know it. And you ain't got to prove it. You just, So it's arctan of x. So it's 4 arctangent of x. Okay? I'm evaluating. This is the improper way of evaluating from negative infinity to infinity. I mean, I should have put b's in there and then take the limit as b goes to infinity, right? But I'm just being kind of sloppy. Anyway, there's the answer to the integral. And there's the, I'm trying to plug in infinity now. So now does anybody know the arctangent of infinity? You guys probably, she said pi over 2. And then I need to do the arctangent of negative infinity. And again, this is just improper. Again, a mathematician watching this video would be pissed off. I mean, what I'm supposed to do is have a b here, and then I'm supposed to take the limit as b goes to infinity. You with me? I mean, infinity is not a number you can plug in. That's why it's improper. So you plug in a b, and you take the limit as b goes to infinity. That's proper. But it's kind of a little semantics in a way, right? Okay. Anyway, the arctangent of infinity is pi over 2. I don't know. How do you know that? Oh boy, let me help you. I mean, do I have to? Let's do trig again. No, not really. Listen, a tangent function. A tangent function looks like this. And it approaches pi over 2 as an asymptote and negative pi over 2 here as a vertical asymptote. Okay, that's true. That's a tangent function. You know what an arctangent function is? It's his inverse. It's like if you took the x and the y and flipped this graph over, you could flip this graph over and an arctangent function looks like this. And it approaches a horizontal asymptote at pi over 2 and a horizontal asymptote at negative pi over 2. Here's a tangent graph, and then this is an arctangent graph. And that helps me do this problem because as x goes to infinity on this arctangent graph, as x goes to infinity, what's the arctangent of infinity? Pi over 2. The y value, it approaches a y value of pi over 2. Times 4 minus, what's the arctangent of negative infinity? Negative pi over 2. What do I have here? I have, that's a 2 pi plus a 2 pi. So this is a 4 pi. You know what? I should have taken off the 4. If I would have taken off the 4, what would this have been?
2 pi.
I don't know. Hang on. With the 4 up there, what's the answer?
4 pi.
4 pi, I think.
Oh, it'd be pi.
So if I took the 4 out of the problem,
It'd be pi.
I think the answer would be pi. That's what I really wanted.
Yeah.
What's this area? Pi. Well, for my problem, it's a 4 pi. This infinite area is not infinite, it's finite, and it converges, and the area is 4 pi. The integral converges. This is a famous integral that converges, and it has a finite amount of area. The area is 4 pi. Cool, huh? I mean, I think it's cool. What I would like is somebody to get me one of these so I could put it on my desk. And then engraved, it could say 4 pi. Yeah. It could be gold, it could be pure gold. Now listen.
I don't think your desk is
it's going to be infinite. It's going to be infinite. It might be tough getting it through the door, but.
The area is 4 pi. You have to measure the area is 4 pi.
I don't want you to leave off any gold. I mean, if you cut it off, rip me off with some gold there, it ain't going to be 4 pi anymore. I mean, that's what's a trip, you know? If you do this from negative 1,000 to 1,000, and it's close to 4 pi, but it's shy. Go from negative 1,000,000 to 1,000,000, and it's a little bit shy of 4 pi, you know? Go from negative infinity to infinity, and then it really is 4 pi. That's what it is. All right. Yes?
So if we were to make this a proper integral, it'd be limit as
Right.
a or
So I did it improperly. Yeah, thank you. So to make it proper, I think I would change it from a negative b to a b.
Okay.
I think that would be a smart way to do it, just because I think I can do it like that, don't you? And then take the limit as b goes to infinity. And then my thought process would be the same down here at the end. I'd be kind of plugging in infinity, but I'd be plugging in b's, and b's going to infinity, right?
Do you care about that one, Tess? Or?
Well, so I showed you, yeah, I think we should do it properly. I showed you how to do it sloppily. But I think my test, I think I'll say, evaluate this improper integral properly. I think I'll put that in my directions. Yes.
Could it work if you just went from 0 to pi and then multiplied by 2 like
Well,
you did in
thank
the other
you.
integrals? Could you, if it's symmetrical?
Sure. She notices that this is symmetrical. She says, let's just go from 0 to infinity and double the answer.
Okay.
Just do half of it and double the answer. You can do that if it's symmetrical, right? Right.
And you said the thing that made it converge is the denominator was much tighter because of the x squared.
Right.
Then it would.
Right.
Okay.
Right. See, what's fun, I don't want to take all your fun away from you, and I don't really want to spill too many beans, so I think maybe I have. But, well, not, I mean, in 8.8, you should investigate some problems. But after investigating some problems, let me just tell you what you'll conclude. This is I mean, you've seen some various different problems here, but one category of problems is these dudes. When you're trying to integrate this 1 over x to the p. And so you saw me do x to the first the other day, and then I did x squared the other day. Today I did x to the 1/4. I did a 4th root of x. But then when you do these problems, there's sort of two problems you can do. You can go from 1 to infinity, or you could do these problems, 1 over x to the p is the function, and you can do these problems from 0 to a number. That's what you saw me do today. You saw me do one from 0 to 16. Remember? I did one, and I shaded this. But so there's these kind of two categories of problems. Let's just focus on one for a second. So these guys, they go from 1 to infinity. So it's this area kind of that you're looking at. And so you know what, I mean, so what you ought to do is do a bunch of these problems. And you know what you should do? You should do 1 over x squared, 1 over x cubed, 1 over x, and see what happens. But I'll tell you what happens. Do you want me to tell you what happens? So when p is a 1, can I say that? When p is a 1, that's this guy?
Yeah.
It diverges. There's an infinite amount of area. But when it's x squared or x cubed, it comes down and it's tighter. It's a little tighter, and all it has to be is bigger than 1, to tell you the truth. So it could be, I said x squared or x cubed, but it could be 1.5 or 1.01. I mean, all it takes is a little power higher than 1, and you dip down, and you're tight enough to where you converge. So what am I saying? I'm saying that when p is greater than 1, it converges. Is that what I just said? When it's x squared or x cubed or just anything, it's going to converge. And when p is less than or equal to 1, it diverges. So that's these graphs. These graphs change. When p is 2 or when p is 3, it gets tighter to the x-axis and they converge. But when p is 1, they diverge. So I'm summarizing this for you. Like I said, I would rather you spent weeks investigating all these integrals and you came to this conclusion yourself. But it's okay. I can drop this hint. Am I making sense? Are you guys okay? I'm there's all kinds of cool improper integrals like this one and this one and this one, but this is kind of one famous category. And what do? They converge when p is greater than 1, and they diverge when p is less than or equal to 1. And it's about this picture and being tight enough to the x-axis kind of to converge or not. By the way, if I investigate this one, this is different. This is from 0 to 1. Is that what I said? That's this. It's still an infinite area, but the rules change a little. I think it's the opposite. I think it's... Okay, hang on. When this was an x squared here, see this x squared? When p was a 2, right? It came down here tighter. See this? Wasn't it tighter? Did I say it was tighter?
Yes.
Look at me. But guess what? When it comes up over here, it's not tighter to the y-axis. So when you try to go from 0 to 1, if p is greater than 1, those guys diverge. Or equal to 1. And when p is less than 1, those are the ones that converge. Over here. That's over here on this picture. It's a different picture. What did I just say? I just said that like a 1 over x squared is tight here, converges here, but look, it's loose here. So it diverges here. What did I do earlier today? I did 1 over x to the 1/4, right? Dude, 1 over x to the 1/4 is loose right here. It's loose. If you did this problem, it would diverge. But over here, it got tight, and we did this problem from 0 to 16, and it converged. We did this problem, and it converged earlier today. I don't know. I'm trying to... I mean, this is just two famous things. I mean, you didn't realize that yet, maybe, but two popular problems, that one and that one. There's other cool problems, too.
So that doesn't have the infinity on it.
Right, there's no infinity, so why
So
is
now
it...
right here.
Hang on,
So
right,
now
why, right, this guy. There's no infinity on it, but why is it improper?
Because you can't have the 0.
The 0, yeah. So it's still this, it's got this improper 0 bound. And it has this infinite area, or maybe not. I mean, it has this infinite looking area, and then depending on how tight it is, it converges or diverges. This category of things. And by the way, I stopped at 1, but I could go to, earlier I did 0 to 16. I mean, it doesn't matter if I... Oh boy. I don't know. I don't want to spend forever here in 8.8 though. It's a cool little topic, and then it's a little bit useful in chapter 9. You know, I only got 7 minutes of class, but I think I want to tell you this. In 9.1, we study sequences. I want to say that a sequence is a function I want to just define a sequence. I want to say a sequence is a function whose domain is the natural numbers, the set of natural numbers. Do you know what I mean by natural numbers?
Yes. 1, 2, 3.
1, 2, 3, 4. Although we could use the phrase counting numbers, but they're defined as natural numbers. Technically, sometimes you do include 0, so then that would be the whole numbers when you. So anyway, the natural numbers usually are 1, 2, 3, but sometimes you can start with a 0. But but you don't plug in a half or 2 or a 3/2 or 2/3. That's not in your domain. You plug in 1, 2, and 3, and then the output is kind of what you stare at. That's the sequence. See, but I don't know. I'm defining it as a function. I could just say, hey man, let's talk about sequences. But it's a function whose domain is the natural numbers. Here it is. We refer to a sequence with a little subscript, and maybe we put a little brace around it sometimes. And so we call this AN. So guess what? You plug in N is 1 first. That's what I said over there. You plug in, what do you get? A1, comma, then you plug in a 2, what do you get? A2, comma, A3, comma, dot, dot, dot. Sometime, at some point, so you might call this A1 the first term. What would you call the A2? The second term, the third term. You know, somewhere down the line you have the nth term. The nth term would just be AN. Hey, what comes after the nth term? The nth plus 1 term. Who's before the nth term? The n minus 1 term. Right? That's right. And then it goes forever. Here, let's look at a specific example. So AN is this sequence, 1 over n. All right, so can you write out some terms of the sequence? What do you start with?
1.
You start with a 1. That's kind of what this says. Unless somebody tells you to start with a 0. By the way, you wouldn't start with a 0 on this one because it's undefined. But you'd start with a 1, and you plug it in, and what do you get? 1, comma, plug in a 2.
1.
And then you're staring at a sequence. What would be the nth term way down here? What would you call the nth term? 1 over n. Good. By the way, when this sequence was presented to you, it was presented to you by giving you the nth term. That's what we're giving you here. We're giving you the nth term, and that helps you find the first term, the second term, the third term. Could you find the 99th term?
1 over 99.
Thank you. Right. Now, real quick, a sequence can converge or diverge. And basically, just real quick, a sequence, AN, converges if the limit as n goes to infinity of AN equals some number L, some number L, where L is finite. In other words, can you take the limit of the nth term and get an answer? And then you know the sequence converges. Otherwise, I guess it diverges. What would you say about this sequence? What's the limit as n goes to infinity of the nth term 1 over n?
0.
Okay, so what could you say about this sequence?
It converges.
It converges, thank you. So this sequence converges. And you know, you could even use the phrase converges to 0 if you wanted this. I mean, it converges to 0. And by the way, you could see that, couldn't you? 1 over 99, 1 over, I mean, right, you could see it heading towards 0. It's not. Okay, that might be enough for now. Just a little quick introduction to sequences. I'll do more. We'll do some more this Friday, maybe. We're at the end of class. That was quick, but thank you guys. I'll see you Friday.